Imagine a world without borders, one colossal continent surrounded by a single, endless sea. Mountains higher than the Himalayas split the horizon, while vast deserts stretched for thousands of miles without rain. In this ancient supercontinent called Pangea, life was both abundant and fragile, shaped by fire, drought, and shifting stone. Here, early reptiles ruled, and forests rose beneath red skies heavy with heat. But beneath its surface, forces were already tearing it apart. How did this united world live, break, and vanish? Step back to the age when Earth was one. The Great Merging, a planet becoming one. In the silence before the continents touched, Earth was a restless mosaic of drifting worlds. Gondwana lay vast and southern, its spine lined with mountains that scraped the sky above the ancient ice of the Permo-Carboniferous. To the north, Laurasia wandered the equatorial seas, trailing chains of islands and shallow reefs. Between them stretched a widening ocean called Rake, a frontier that would one day close. Over hundreds of millions of years, slow and unseen, these colossal fragments inched together at the pace of growing fingernails. Beneath the shifting plates, the mantle churned like a hidden tide. Hot plumes of rock rose from the core mantle boundary at rates of only a few centimeters each year, carrying with them the energy that sculpted mountains, birthed volcanoes, and shifted continents. Seismic tomography, the planetary equivalent of a CAT scan, has revealed the fossilized ghosts of ancient subduction zones buried hundreds of kilometers deep. The eventual collision was inevitable, a meeting written into the slow rhythm of convection and gravity. The Rake Ocean began to vanish as the edges of the continental masses converged. Sediments that had once rested quietly on the seafloor were scraped upward, crushed, and folded into towering ranges. In present-day Europe, the Varuscan and Hercynian orogenies mirrored this violence, uniting what would become the ancient cores of France, Germany, and Poland. Radiometric dating of metamorphic minerals from these regions shows ages clustering around 320 to 330 million years, a geological signature of continents becoming one. To the south, Gondwana was a continent of extremes, composed of what are now South America, Africa, Antarctica, Australia, and India. It bore the imprint of the late Paleozoic Ice Age. Thick glacial deposits, known as tillites, stretch across all these lands today, a fingerprint of their shared past. Dropstones embedded in ancient marine sediments record the advance and retreat of continental glaciers that reached nearly to the equator. Its northern journey closed the Rheic and Tethys oceans while pushing against Laurasia's southern shores with unrelenting force. By 335 million years ago, the world had entered the Carboniferous, an age of high oxygen and verdant abundance. The swamps and forests that blanketed equatorial Laurasia produced thick seams of coal that would one day fuel the fires of human industry. As Pangea formed, these tropical zones began to shift and contract under the weight of colliding plates. Fossil spores and leaf imprints from this period reveal the transition from wetland floras dominated by lycopods and ferns to more drought-tolerant seed plants such as conifers and pteridosperms, an early ecological adaptation to continental unity. The process of merger was not gentle. Where the continents met, the crust thickened to twice its normal depth, deforming and heating under the strain. This generated vast belts of metamorphic rock, rich in mica and garnet, which today gleam from mountain outcrops across Appalachia and the Urals. Deep beneath the surface, molten magma intruded along fractures, cooling into granite bodies that would later anchor the continental cores. Uplift exposed these rocks to erosion, feeding rivers that carried sediments across thousands of kilometers. The ocean that surrounded this growing landmass, Panthalassa, reflected the light of a younger sun across a horizon that seemed endless. The collision of continents altered ocean currents, changing the distribution of heat and moisture across the globe. Computer models of late Paleozoic circulation suggest that with fewer coastlines and enclosed seas, global climate became more extreme: hot equators, cold poles, and vast regions of still air that trapped dust and heat. The stage was being set for the supercontinent's defining paradox. Unity would breed isolation. Evidence of this climatic shift lies preserved in the rocks. Evaporite deposits in the interior basins of what are now the southwestern United States, Morocco, and Central Asia show that as the landmass grew, rainfall declined dramatically. Layers of gypsum and halite, crystallized from drying inland seas, record seasonal rhythms of drought and flood. Isotopic studies of oxygen and carbon from these minerals indicate intense evaporation under scorching summer suns, interrupted by brief monsoons that delivered torrents of rain. In the fossil record, species distributions began to mirror the geography of collision. Once separated marine ecosystems mixed, producing both evolutionary opportunity and extinction. Trilobites, ancient icons of the Paleozoic seas, dwindled as shallow habitats vanished. Terrestrial faunas, on the other hand, spread freely across the new land bridges, creating continental-scale biomes. The synapsids, ancestors of mammals, expanded from South Africa to Russia, while amphibians radiated through tropical swamps. The merging continents created corridors for life, but also barriers for migration as deserts and mountain chains grew. As mountain belts rose, they influenced rainfall patterns, casting immense rain shadows and redirecting river systems. The ancestral Amazon may have once flowed westward into what became the Pacific margin of Gondwana, before the uplift of the Andes reversed its course. These geological rearrangements are captured in the paleogeographic maps constructed from paleomagnetic data records of ancient magnetic poles frozen into iron-rich minerals. By the Permian period, around 299 million years ago, Pangea had reached its full expression, a supercontinent spanning nearly one-third of Earth's surface. Its formation marked the culmination of a cycle known as Wilson's cycle, the rhythmic opening and closing of oceans through plate tectonics. Every 400 to 600 million years, the planet undergoes such unification and fragmentation. The creation of Pangea was but one iteration in this vast geological pulse. For a moment in deep time, all rivers led to one ocean, all winds crossed one land. The continents, once solitary wanderers adrift in darkness, had found one another. Yet in that grand union lay the seeds of division stresses stored in the crust, mantle plumes waiting below, and climates pushed to their limits. The earth had become one body, but it would not remain whole for long. In the stillness that followed the final collision, deserts began to form, skies thickened with dust, and the heartbeat of the planet slowed into a new rhythm. The great merging was complete, and the age of isolation was about to begin. Landscapes of giants, the interior of Pangea. Now the land stretched unbroken from horizon to horizon, a single continent shimmering beneath a pale sun. What had once been a patchwork of drifting worlds was now fused into a single, colossal heart, immense, airless, and far from the breath of the sea. Winds crossed thousands of kilometers without pause, sweeping grains of ancient quartz into towering dunes that rolled endlessly across what would one day become North Africa and Western North America. In the interior of Pangea, the sky was not blue, but veiled in pale haze, a world both eternal and eroding at once. When the sun reached its highest glare, even shadows seemed to dissolve. The temperature between day and night could swing by more than 40 degrees Celsius, an effect born of land too wide for the ocean's moderation. Sedimentary cores taken from the Permian basins of Sonora, Texas, and the Sahara reveal sequences of oxidized sandstones, hematite-stained red beds that formed in extreme aridity. Each layer speaks of a climate sealed away from moisture, where rainfall may have fallen only once in a decade. If rain ever came here, it arrived in torrents that erased the horizon. Rivers would swell suddenly, carving new channels across the dunes before vanishing within days. In the rock record, these ephemeral floods are preserved as thin strata of conglomerate lenses and mud-cracked clays, flash flood deposits that punctuate the otherwise endless sand. Paleosol analysis from these layers shows calcrete horizons rich in calcium carbonate, evidence of long dry seasons where groundwater rose and evaporated again and again. Geochemical measurements of oxygen isotopes in these carbonates indicate surface temperatures that often exceeded 45 degrees Celsius, with atmospheric carbon dioxide concentrations 4 to 6 times higher than today. The interior basins of Pangea were like inland seas without water. Cross-bedded sandstones within these formations preserve the directions of ancient wind lines carved into stone that show consistent patterns of trade winds blowing from east to west. Global circulation models, reconstructed from these formations, reveal a super monsoon system, one so large it enveloped half the planet. During summer, the continental interior heated faster than the ocean, drawing moist air inland, while winter brought the reverse, with air rushing back toward the coasts. Moisture died in transit, leaving a world ruled by heat and wind. Core samples from the Pantalassan seafloor contain microscopic grains that match the mineral fingerprint of Pangean deserts, evidence that storms carried particles across thousands of kilometers. These dust storms would have dimmed the sun and shifted global albedo, cooling some regions while baking others. In this way, even the emptiness of Pangea's heart influenced the rhythm of the entire planet. The geological record tells of alternating cycles of dryness and short-lived humidity, recorded in thin laminae that reveal seasonal breathing wet and dry, expansion and retreat, the pulse of a supercontinent alive with contradiction. In this silence, creatures moved at dusk and dawn, their footprints pressed into soft mud that hardened under the next day's heat. Fossil trackways from the Tumblr sandstone of Western Australia and the Coconino sandstone of Arizona reveal the passing of small reptiles and amphibians across dune slopes, their gait patterns preserved in exquisite detail. The creatures themselves are gone, but their brief crossings remain, locked within the geometry of wind-blown stone. Core samples from the Karoo and Sonora basins reveal another layer of the story, the chemistry of ancient air. Stomatal density counts from fossilized leaves found in marginal deposits indicate steadily increasing carbon dioxide levels through the late Carboniferous into the Permian. These data correspond with volcanic outgassing events and the slow collapse of Pangea's carbon sink as tropical forests declined. The once lush equatorial wetlands that had flourished in the previous era vanished beneath expanding dune fields, their extinction marking a planetary shift from oxygen-rich stability to the unstable atmosphere that would later feed extinction. The dunes themselves were monumental, some over 300 meters high, stretching in chains for hundreds of kilometers. Wind direction and speed can be reconstructed from the angle of crossbeds within these formations. In the modern analogue of the Namib Desert, researchers find that similar dune geometries correspond to sustained winds of 30 to 40 kilometers per hour. Applying these models to ancient strata suggests that Pangean winds may have reached gale strength for months at a time, driven by thermal contrasts between the interior and the coast. The relentless abrasion polished quartz grains into perfect spheres, their uniformity a geological testament to duration and distance. When the wind paused, the land glowed red beneath a waning sun. Desert varnish, a thin layer of manganese and iron oxides, coated exposed rocks, darkening them over millennia. The chemical ratios within these coatings, measured today by microprobe analysis, show that even oxidation had its rhythm, tied to cycles of humidity and dust accumulation. Nowhere else on Earth has emptiness carried such memory. The fossilized dunes of the Coconino, the redbeds of the Thuringian Basin, and the salt flats of central Pangea are the archives of a world both unified and divided, a single landmass, fractured by climate instead of by plate. Life retreated to margins, the coasts, the rift valleys, the shadowed canyons, where groundwater still whispered beneath stone. The same forces that had joined the continents had also created an interior beyond the reach of the sea, a place where evolution waited, patient and enduring, for the promise of rain. As the sun set over this vast desert, the light bent low through suspended dust, igniting the air in hues of copper and gold. Somewhere beyond the shimmering horizon, rivers still flowed, and oases bloomed in silence. In the still heat of the interior, the story of life was not over but merely paused. Beneath the cracked earth, seeds endured, spores clung to damp rock, and roots slept in the soil's last moisture. The world had not died, it was holding its breath. Soon, among the edges of this desolation, the first green veins would begin to reappear fragile, luminous, and alive against the dust. Oases of life, the green veins of a dying land. Yet, in the lowlands where the dust settled thickest, something stirred. Shallow waters gathered in ancient basins, catching the brief breath of rain that still remembered the sea. Beneath the relentless heat, roots slept in the soil, spores clung to the undersides of stones, and each drought carried within it the memory of wet seasons long past. These were the refuges of Pangea's heart, rare sanctuaries where the supercontinent's desolation was pierced by persistence. Rivers bled across the stone plains in erratic pulses, guided not by steady rain, but by the whims of a monsoon cycle that reached deep into the continent's core. Each season, torrents cut through ancient floodplains, spreading silts rich in iron and clay that glowed crimson beneath the sun. Fossilized sediments from the Karoo Basin tell of alternating rhythms, mud layers streaked with gypsum, siltstone rich in plant debris, and desiccation cracks that preserved the dance between abundance and absence. It was in these places, fleeting yet fertile, that the planet's biological pulse continued to beat. Glossopteris, a tree-like fern that had once carpeted the southern continents, now persisted in scattered enclaves, its broad leaves designed to trap light and conserve moisture. Fossilized roots, known as vertebraria, record the story of their endurance-thick, segmented structures that stored water beneath the surface like buried lungs. Around them grew dicroidium and early cycads, pioneers of resilience whose seeds bore protective coats against heat and drought. In the scattered wetlands of Pangea's south, these plants formed miniature forests, green only in brief intervals, each cycle leaving behind a new layer of carbon-rich soil that still darkens the rock record today. Mud cracked and reformed beneath the slow tread of creatures that had learned to move between flood and famine. Amphibians, descendants of Devonian pioneers, sheltered in the margins of shrinking pools, their bodies pressed against the cool mud until the rains returned. Fossil burrows from the Karoo and Chinle formations reveal chambers lined with hardened clay refuges, built by early therapsids such as Lystrosaurus, creatures that could outlast the dry months in dormancy. Insects traced fine hieroglyphs across the sediments, wing cases, bite marks, and pollen trails that mark the earliest known pollination behaviors. Life's persistence here was written not in triumph, but in patience. Geochemical studies of Triassic soils reveal a landscape balance between survival and collapse. Oxygen isotope ratios within fossilized root systems indicate a climate oscillating between intense droughts and short-lived wet seasons. Evaporite layers testify to the dominance of aridity. Yet within them lie thin strata of freshwater deposits where algae once bloomed. In northern Pangea, carbon isotopes tell of vegetation responding to rising carbon dioxide levels, a greenhouse counterpoint to the cool interiors of ancient Gondwana. These data sketch a portrait of contrast the Earth, both heating and drying, yet alive with regional variability, its climates as patchwork as its soils. Each discovery, each measured ratio, narrows the distance between rock and memory, revealing the hidden pulse of ecosystems that refuse to fade. On the continent's western margins, where ocean moisture occasionally crept inland, swamp forests endured. Fossilized trunks found in the Newark supergroup of what would become eastern North America, record-dense stands of Araucarioxylon, early conifers that rose above fern undergrowth like living towers. Their resin hardened into amber, capturing within it the remains of Triassic insects and spores. In the same sediments lie imprints of horsetails and lycopods, echoing the persistence of lineages born in Carboniferous swamps, but now transformed by drought-tolerant evolution. The air above these forests would have shimmered with clouds of primitive dragonflies, while amphibians and small archosaur reptiles hunted along the shaded margins of pools. Far to the east, coastal belts that rimmed the Tethys Ocean formed another chain of life deltas, estuaries, and tidal marshes where the land remembered its marine origins. Fossil evidence from what is now Morocco, India, and southeastern China shows vegetation adapted to brackish conditions. Mangrove-like trees, dense mats of algae, and early seed ferns anchored in tidal mud. Here, the influence of the ocean brought moderation to the climate, fostering more complex food webs. Fish ventured upriver into estuaries, while amphibians and reptiles transitioned fully to land, testing new ecological boundaries. These coasts served as evolutionary corridors, green borders where ocean and continent wove life together. Geologists reconstructing these environments have traced rhythmic layering in the rock record that matches the beat of ancient monsoons. Seasonal floods left alternating dark and light sediment bands, capturing each cycle like pages in a planetary diary. Computer models suggest that vast pressure systems formed over the continental interior, drawing moisture from the Tethys Sea into short-lived deluges that revived the oases. For weeks, rain transformed dust into marsh, awakening spores, rehydrating cyanobacteria, and calling forth blooms of vegetation visible even from space if eyes had existed to see. Then, the cycle would reverse, and the land would harden again, sealing its secrets until the next breath of rain returned. Even in the most parched regions, where dunes towered hundreds of meters high, life found invisible pathways. Microbial mats grew in thin films of moisture beneath the surface, their structures preserved today as fossil stromatolites. Within their cyanobacterial filaments, nitrogen was fixed and carbon trapped, forming the microscopic foundations of ecosystems that would one day nurture vertebrate evolution. These quiet chemistries turned wastelands into laboratories of survival, showing that even under the harshest skies, the machinery of life never fully stopped. Life, it seemed, did not need mercy, only persistence. Across millions of years, it adapted to scarcity, rewriting its own boundaries each time the earth grew unkind. The green veins of Pangea were not lush, not abundant, but they were alive, and from them the next wave of evolution would rise. As drought gave way to endurance, and endurance to adaptation, these oases became the incubators of the great creatures yet to come. The wind still carried the memory of rain, and beneath the cracked crust of a dying land, the first roots of tomorrow were already stirring. Lords of the land, the rise of the synapsids, from the oases, life rose and walked. What had once clung to mud and shadow now strode across the plains in flesh and muscle. The green veins of survival had birthed creatures of bone and fire, the synapsids, rulers of the dry kingdom that Pangea had become. Across the scarred interior of the supercontinent, the wind carried dust and the low tremor of movement. Herds of thick-bodied herbivores grazed upon sparse vegetation, while predators, sleek and heavy-shouldered, prowled the edges of floodplains that shimmered under the red sun. For a brief geological heartbeat, these beings were the undisputed sovereigns of the land, their forms strange yet prophetic, the ancestors of mammals, the heirs of the resilience that had endured through drought and storm. They hunted beneath crimson skies that glowed through veils of suspended dust. Across the flatlands of the Karoo and the plateaus of what would one day become Russia and China, the earth thrummed with life of astonishing diversity. Gorgonopsians, their skulls long and narrow, moved with a predator's certainty, their saber-like canines glinting in the haze. Nearby, herds of dicynodonts shuffled in loose ranks, their beaked mouths tearing at hardy seed ferns, their tusks gleaming like ivory in the light. Between them, smaller forms, Thrinaxodon, Procinosuchus, and Biarmasuchus, darted between burrows and roots, bridging the boundary between reptile and mammal. This was the age of flesh in flux, when anatomy itself was an experiment written across millions of years of trial and persistence. Fossil beds from the Karoo Basin, the Ural Mountains, and the basins of Yunnan speak in bones that have endured the erosion of epochs. There, paleontologists uncover skeletons arranged in final moments, predators locked in the curve of pursuit, herbivores collapsed beside their young, and burrows sealed by ancient floods. These discoveries reveal not only who lived, but how. Thin sections of fossil bone, studied under polarized light, show vascular canals, evidence of elevated metabolism and warm-blooded tendencies. Microscopic growth rings mark seasonal rhythms, revealing creatures capable of enduring environmental oscillations. Through these fragments, science reconstructs not monsters, but pioneers of biological transformation, beings whose every adaptation pushed life closer to the mammalian form. Their jaws hinged with precision, and their teeth spoke the language of efficiency. Where the reptiles of earlier ages had jaws lined with uniform fangs, the synapsids evolved differentiation incisors for nipping, canines for piercing, molars for grinding. This innovation changed everything. It allowed them to process more food with less effort, to sustain larger bodies and higher energy demands. The structure of their skulls reveals the defining mark of their lineage. A single temporal opening behind the eye socket, a window through which powerful jaw muscles attached. This anatomical trait, the synapsid hallmark, became the foundation upon which all mammalian complexity would rise. In these creatures, one can see the beginnings of the face, not of dragons or reptiles, but of kin. Bone and muscle told of evolution's relentless craftsmanship. Gorgonopsians were built for pursuit, their limbs held closer beneath their bodies than the sprawling reptiles they hunted. Their chests expanded with deep rib cages that hinted at greater lung capacity. Inostrantsevere, among the largest of them, reached lengths of over 3 meters, a hunter of both speed and precision. In contrast, the dicynodonts, squat and herbivorous, developed powerful shoulders and beaked jaws for rooting through dry vegetation. Their skin, reconstructed from fossil impressions, may have been tough and hairless, better suited to the arid climate. These were ecosystems of tension and equilibrium, predator and prey sculpted by the same relentless elements. The fossil record also preserves moments of intimacy that speak across time. In the Karoo, a Thrinaxodon pair was found curled together in a shared burrow, their skeletons intertwined as if in shelter from a sudden flood. Another specimen was discovered in proximity to fossilized eggshell fragments, a rare glimpse into early parental behavior. Burrow casts show chambers divided into sleeping and nesting sections. hinting at social organization and care uncommon in reptiles. Such findings blur the line between instinct and emotion, suggesting that by the Permian, the roots of mammalian behavior, warmth, protection, cooperation had already begun to take hold beneath the unforgiving sky. Geochemical studies from Permian strata reveal the environmental pressures that shaped their evolution. Oxygen isotope data from fossilized carbonate nodules indicate wide climatic swings, from monsoon-fed wetlands to hyper-arid deserts. Synapsids adapted through physiological flexibility. Some developed burrowing lifestyles to escape heat, while others, like Synagnathrus, roamed open plains where seasonal rains returned briefly to awaken vegetation. Bone histology supports this adaptive narrative, showing varied growth rates among species rapid in predators, slower in drought-resilient herbivores. In this dynamic equilibrium, life experimented endlessly with endurance. Paleontologists have mapped their range across nearly every corner of Pangea. Trackways preserved in the red beds of South America, fossil burrows in Antarctica, and skeletal remains in India and China confirm that the synapsids were not confined to a single environment. They spanned continents, thriving in both equatorial forests and polar floodplains. The interior deserts, though harsh, offered seasonal abundance that sustained herds, while coastal margins provided refuge during the planet's climatic extremes. Through this global dispersal, the synapsids achieved what few clades ever had: ecological domination. Yet beneath this triumph, the planet stirred. Deep within the crust, volcanic forces gathered along the fissures that would one day fracture Pangea's unity. The land began to tremble with the first whispers of catastrophe. Ash and gas seeped into the atmosphere, darkening skies, altering rainfall, and setting in motion the slow collapse of ecosystems. The fossils record the signs: a sudden decline in species diversity, thinner growth layers in bone, and interrupted sedimentation where rivers once flowed. The reign of the synapsids, though grand, was built upon fragile ground. Every empire of life believes itself eternal. For millions of years, the synapsids ruled beneath the red sun, shaping the earth with their hunger and their endurance. Their bones lie now in the sandstone of forgotten basins, silent witnesses to a vanished dominion. Yet from their forms, the blueprint of all mammals, was born the breath, the warmth, the heartbeat that endures even now. The plains that once echoed with their steps would soon fall silent, awaiting the next age to rise from the ashes. Beneath the crust, the fire that united and divided. While the synapsids strode across the sun-bleached plains of Pangea, an unseen force was gathering below them. The earth beneath their clawed feet was not still but alive, breathing through slow convulsions of pressure and molten ascent. Beneath the sandstone and clay of ancient floodplains, the planet's heart burned with a fever older than the continents themselves. Heat, trapped deep within the mantle, began to surge upward in plumes, immense columns of molten rock, rising like ghosts of creation. Far below the crust, the mantle convected in slow, immense spirals. Each cycle took millions of years, carrying heat outward from the metallic core and reshaping the crust above. In the Permian world, these convective cells began to change direction, warping the base of Pangea like a vast, shifting lung. Beneath what would one day become Siberia and central Gondwana, mantle plumes thickened superheated upwellings that pressed against the lithosphere until fractures spidered through the crust. Geologists, reading the magnetic signatures of ancient rocks, now trace these early stresses, finding in their alignment the first tremors of division hidden beneath unity. In places, the crust responded with rifts, deep, narrow valleys where the land stretched and thinned. These scars, found today in the Karoo Basin of South Africa and the Paraná Basin of Brazil, reveal the slow agony of a world under tension. Layers of basalt, preserved like black glass, mark where magma once broke free and cooled in contact with the air. Radiometric dating of these layers places their formation at the very twilight of the Permian, between 252 and 260 million years ago. What scientists call the Siberian traps would one day bear witness to the culmination of this unrest. Spanning over 7 million square kilometers, they were not mountains but plateaus of fire formed when molten basalt flooded the surface in relentless waves. The eruption lasted nearly 1 million years, releasing an estimated 4 million cubic kilometers of lava and a staggering quantity of gases: carbon dioxide, methane, and sulfur dioxide. The skies darkened with aerosols, the seas acidified, temperatures soared by 5 degrees Celsius or more. It was not a single explosion, but a planetary exhalation that would test the resilience of all life above. Before this cataclysm fully unfurled, however, the signs were already there. In sedimentary rocks that once bordered Permian wetlands, paleontologists have discovered thin layers of volcanic ash interbedded with fossilized plant remains. Chemical analysis reveals spikes in mercury, a signature of distant eruptions and degassing events. Even the fossilized growth rings of trees tell of stress, with irregular spacing hinting at changing climates and erratic seasons. The heat rising from within did more than destroy. It reshaped the face of the continents, forming new landscapes as it burned through the old. As magma intruded through cracks in the crust, it baked coal seams and sedimentary layers, releasing yet more greenhouse gases. Vast igneous provinces sprawled across Pangea's surface, connecting regions that had once been separated by shallow seas. The unity of Pangea was, in truth, an illusion, a momentary stillness in a cycle of merging and division that had governed Earth since its beginning. Scientists studying modern tectonic systems find echoes of that restless age beneath our feet today. The African Rift Valley, with its spreading basins and volcanic fields, mirrors the early fractures of Pangea's interior. Seismic tomography imaging the planet's mantle through earthquake waves reveals hot upwellings beneath the same regions that once bore Permian eruptions. What began under Pangea did not end with it. The fire never truly went out. The temperature of Earth's core during that era is estimated to have been several hundred degrees hotter than it is today, driving more vigorous convection and thinner crust. Isotopic evidence from zircon crystals, dated with uranium lead decay, supports the idea of intense thermal flux beneath supercontinents. The heat trapped beneath such a vast unified landmass could not dissipate easily. The mantle plumes, lacking release, built pressure until the crust itself became the vent. This feedback between unity and heat may explain why every supercontinent eventually breaks apart. For the living world, these deep convulsions carried invisible omens. Volcanic gases drifted through the atmosphere, altering photosynthesis and carbon cycles across the globe. In marine sediments from what is now China and Greenland, carbon isotope ratios record dramatic shifts, evidence of ocean acidification and declining oxygen. The land grew hotter, the air heavier, the rains more acidic. To the synapsids that ruled the plains, the air itself began to change. Ecosystems that had flourished for tens of millions of years started to collapse beneath a slow, unseen poison. Yet even in destruction, there was transformation. The fires of the mantle forged new minerals, new chemical pathways, new beginnings in the ruins of the old. When lava met seawater along the margins of the supercontinent, it produced pillow-basalts, glassy, bulbous formations that today lie buried beneath layers of sediment, silent witnesses to the first attempts of the ocean to reclaim the land. In those places, new crust was born, darker and denser, the early outlines of the basins that would one day divide the continents again. As the eruptions waned, the air cleared only briefly before the greater consequence became clear. the biosphere had been reset. The Permian-Triassic extinction, often called the Great Dying, eliminated over 90% of marine species and 70% of terrestrial ones. Its cause lay beneath the crust, in the vast, sustained pulse of volcanic activity that began when Pangea's heart overheated. The Earth had created Pangea in the name of balance, and in seeking equilibrium, it found chaos. Even now, the remnants of those ancient fires whisper through the rocks. Magnetized minerals in basalt flows retain their orientation to a vanished pole. Trapped gas bubbles hold the chemistry of vanished skies. Through them, scientists reconstruct not only catastrophe, but the logic of a living planet, the cycle of merging and breaking, of crustal unity and molten division, reveals Earth as a being with memory, one that endures by remaking itself. And above it all, as the last of the great synapsids walked under reddened skies, the first fractures of the supercontinent widened into rifts that would one day fill with seawater. The planet that had once been one began to dream again of oceans. Beneath the crust, the fire still moved, patient and unending, preparing to carve new worlds from the ashes of the old. The endless ocean, Panthalassa, and the edge of the world. When the fires of the deep at last subsided, the world exhaled. Steam rose from the fractured crust, curling upward into a pale sky, and in every direction beyond the broken edges of Pangea stretched a boundless expanse of water. Panthalassa, the universal sea, encircled the supercontinent like a ring of blue eternity. From horizon to horizon, there was only the glitter of sunlight and the slow rhythm of waves. Distant from the planet's molten heart, the ocean stretched as its living frontier. Beneath its mirrored surface lay mountains taller than Everest, trenches deeper than any canyon carved by air or ice. The mid-ocean ridges of Panthalassa formed a sprawling labyrinth of volcanic summits and spreading crust, built by the same convective forces that had united the continents. Magnetic minerals locked in these ancient basalts now traced the slow migration of the seafloor, proof that even this vast ocean was alive with motion. In the deep rock, scientists have read the ghost signatures of ancient reversals of the Earth's magnetic field, each line a memory of time inscribed beneath a drowned world. In the shallows, near the continental margins, sunlight reached through water that was warm and clear. Coral-like organisms flourished where conditions allowed, though true corals, as we know them today, had not yet arisen. Instead, the reefs were built by sponges, algae, and bryozoans, creating labyrinthine fortresses of life. Fossil beds, along the edges of what is now Western North America and Japan, reveal these ancient reef systems, teeming with brachiopods, ammonites, and early bony fish. Their shells and skeletons still preserve the chemical record of seawater temperatures, a silent archive of a world balanced precariously between stability and change. The upper ocean shimmered with plankton blooms, their photosynthetic pigments turning sunlight into sustenance for the vast food webs below. Radiolarian microfossils, found in the deep cherts of ancient Panthalassan crust, reveal the rhythm of these microscopic cycles, how carbon was drawn from the air and buried in the sediments of the sea floor. It was through these tiny architects that the atmosphere itself began to breathe in synchrony with the sea. Each bloom drew down carbon, each death sent it sinking into darkness, feeding an unseen balance that shaped the planet's climate for millennia. Where light faded to black, the ocean transformed. At depths beyond 2 kilometers, the temperature dropped close to freezing and oxygen grew scarce. Here, only the hardiest life endured, worm-like creatures, thin-shelled mollusks, and microbial colonies that fed on chemical energy rather than sunlight. Sediments from these ancient depths, now uplifted in modern mountain ranges, show layers rich in pyrite and organic carbon, evidence of widespread anoxia. The Panthalassan deep was not a single void, but a stratified living machine cycling nutrients and gases on a scale beyond comprehension. The waters never rested, their loops drew the planet into motion. Without major barriers of land, the winds and tides drove vast gyres that wrapped the equator, transporting heat across hemispheres. Models of Permian ocean circulation suggest immense stability at the surface, but stagnation below. The deep waters turned slowly, starved of oxygen, accumulating gases that would one day rise and change the world above. To scientists today, their traces are found in isotopic ratios in the subtle variations of carbon and oxygen that mark the tempo of a changing planet. Away from Pangea's coasts, the world dissolved into endless blue. With no nearby land, nutrients were scarce, and biodiversity thinned across thousands of kilometers. The fossil record shows that Panthalassa's vastness was both cradle and cage. Species evolved in isolation, confined to narrow ecological zones. The size of the ocean itself limited evolution, creating stretches of biological stillness across its surface. But life refused silence, beauty rose from emptiness. Schools of early ray-finned fish glimmered near the surface, feeding on clouds of plankton that drifted with the currents. Nautiloid predators hovered in the gloom, their coiled shells reflecting the dim, refracted light. In the calm shallows, trilobites still clung to survival, their numbers dwindling with every passing epoch. What the land suffered in fire, the ocean endured in silence, a slow suffocation that left no scars but changed the chemistry of life itself. Where volcanic islands pierced the surface, life found footholds anew. These islands, ephemeral and shifting, offered havens for species that drifted on oceanic currents or clung to floating debris. The fossilized remains of such island arcs, now scattered across the Pacific Rim, speak of Panthalassa's restless geology, a realm in constant renewal. Through these island worlds, winds carried dust, spores, and organic matter, linking ocean and continent in invisible exchange. Even the air above the water bore witness to the sea's moods. When carbon dioxide rose from volcanic vents or escaped from warming waters, it changed the very composition of the atmosphere. Sulfur, aerosols, and methane plumes formed transient veils that dimmed the sun and cooled the earth before vanishing again. Each alteration echoed upward through wind patterns, through rainfall, through the faint chemistry of clouds. What began in the depths would soon rise into the sky, the next chapter of transformation written not in rock or coral, but in the invisible currents above the world. At the edge of the supercontinent, where Panthalassa met the deserts of Pangea, the boundary between land and sea blurred. There, tidal flats stretched for kilometers, covered in microbial mats that shimmered with green life. These mats, preserved as stromatolites in ancient limestone, recorded the meeting of two realms, the last refuge of the photosynthetic pioneers who bound carbon, built oxygen, and prepared the way for all who would follow. And still, the ocean stretched outward, silent, radiant, immeasurable. It was the mirror of all things, the memory of the earth before division. Beneath its surface, the planet stored its future, waiting for wind and air to join the dialogue of change. Soon, what stirred within the sea would ascend to the sky, and the unseen forces above would begin to reshape the fate of life itself. Winds of change, the climate engine of a supercontinent. At first, there was only silence, a heavy, suspended quiet over the boundless ocean of air. Slowly, almost imperceptibly, heat began to move. It rose from the baked surface of the supercontinent and met the cool breath of the encircling seas. The sky shivered, then began to stir. Winds were born not from chaos, but from imbalance, the Earth's eternal response to difference. Thus began the long breath of Pangea, a planetary exhalation that would shape every life and every storm that followed. At the height of its existence, Pangea stretched nearly pole to pole, a single continent so immense that its center never felt the ocean's touch. Here, sunlight struck for months with no relief, while the distant poles shivered in darkness. Between them, colossal pressure gradients formed. The result was a new kind of atmospheric engine, a system of global monsoons that dwarfed anything the planet had known before. To understand this world is to imagine weather unbound by modern limits. The summer hemisphere boiled under vast convective towers that stretched miles high, drawing moist air from the coasts and releasing it as torrents on the outer edges of the land. Then, as the seasons turned, those same regions fell silent and cold. Winds shifted course, reversing their flow, leaving behind deserts cracked by alternating flood and famine. Fossil evidence tells us the story of these rhythms. In red and ochre bands of sediment, the remnants of Triassic and Permian floodplains, scientists find traces of alternating wet and dry cycles. Each layer marks a pulse of climate, a heartbeat of the supercontinent's air. Mud cracks from ancient lake beds record seasons of evaporation. Ripple marks frozen in stone reveal brief returns of rain. The rocks remember the wind as much as the creatures that once breathed it. Near the polar frontier, the warmth of Pangea surrendered to ice and wind. Here, the supercontinent's configuration twisted the global circulation into extremes. In summer, endless daylight melted shallow ice and filled lowlands with ephemeral swamps. In winter, the cold returned with brutal precision, plunging temperatures far below freezing. Yet even there, forests of conifers and ferns persisted hardy survivors of the shifting tilt of Earth's axis. Rings in fossilized wood show the scars of these cycles, wide bands of rapid growth under warmth, followed by narrow, dark lines of dormancy in cold. For the creatures that roamed these lands, the synapsids, reptiles, and amphibians of the Permian world survival meant mastering movement. The great interior deserts of Pangea were deadly in their constancy, yet the edges of floodplains offered brief abundance. Fossil trackways record migrations, trails pressed into wet clay during short-lived seasons of rain. Some led toward vanished rivers, others toward evaporating basins where salt crystals grew like frost. This haze cooled the surface slightly, a subtle feedback that linked earth, air, and light in an unending exchange. The immense scale of Pangea's climate also influenced the chemistry of the air itself. As vegetation spread and died across this unified continent, the atmosphere's balance of oxygen and carbon dioxide fluctuated wildly. During the late Permian, oxygen levels fell dramatically, reaching as low as 15%, a drop that strained even the hardiest lungs. Heat and aridity increased, amplifying fires that swept through conifer forests and left blackened charcoal in the sediment record. These fires released carbon back into the air, accelerating the warming. The Earth, for a time, became its own furnace, locked in cycles of feedback that tested the limits of adaptation. High above, the jet streams of the ancient world moved differently from today. With no divided oceans to steer them, these currents wrapped the planet in broad, undulating belts. Dust from the central deserts drifted across hemispheres, settling in what would one day become South America, Europe, and Australia. Traces of this wind-borne silt remain in the mineral signature of Permian rocks, silent testimony to an atmosphere vast enough to move mountains of sand through the sky. In this sense, the air was both sculptor and witness, reshaping the face of Pangea grain by grain. In the churn of endless cycles, meaning hinged on the smallest shift, a slight shift in Earth's orbit or axial tilt might intensify the seasons, magnifying floods and droughts across the landmass. These astronomical rhythms, Milankovitch cycles, as they are known today, modulated the flow of sunlight and thus the breath of the planet. The sedimentary record reveals their fingerprints in repeating patterns of deposition. Thick beds of silt followed by thin layers of dust, echoing the alternation of monsoon and dry wind across tens of thousands of years. Even in deep time, the pulse of the cosmos could be read in the language of climate. There is a strange poetry to this kind of planet, one where air itself became a sculptor of worlds. For millions of years, the breath of Pangea defined what lived and what vanished. Ecosystems rose on the tides of wind, only to fade when the currents changed. Yet within this instability, life learned resilience. Seeds evolved tougher coats. Animals developed ways to burrow, migrate, or wait out the extremes. The climate engine, that once seemed merciless, became, in time, the architect of innovation. It taught the biosphere to bend, not break. Now, as we trace the faint signatures of those ancient winds in stone and isotope, we hear an echo that feels hauntingly familiar. For though the continents have long since drifted apart, the same global breath continues reshaped but unbroken, a memory of heat and motion encoded in the air we breathe today. The story of Pangea's atmosphere is not one of destruction alone, but of endurance, a reminder that even the stillest air hides the power to transform a planet. And somewhere, above the relic deserts that once formed its heart, the wind still moves, whispering through rock and canyon, across oceans that have replaced the ancient plains. It is a continuity of sound, a soft resonance between epochs. From that invisible current, the journey will next turn upward, toward the sky itself, where the creatures of Earth learn to harness the air and claim it as their own. Wings of survival, the invention of flight. From the still breath of Pangea's deserts, life began to move differently. In the shadows of withered forests, where air once only carried dust, new forms learned to ride it. The winds that had once shaped continents now pressed against the membranes of creatures light enough to rise, and the atmosphere itself became a new arena for survival. Across the supercontinent's interior, where the heat shimmered and rivers dried to salt scars, evolution turned its gaze upward. Trees grew far apart, their crowns skeletal and sun-bleached, their trunks home to insects that had themselves already mastered flight for millions of years. Vertebrates, bound to the ground for eons, began to mimic what the air had long carried. Fossils from what would become Germany, Madagascar, and the Urals show the earliest evidence of vertebrate gliders reptiles, with ribs stretched into elongated struts, supporting delicate membranes of skin. Coelurosaurus, sometimes called the gliding lizard of the Permian, unfurled its living sails across dry updrafts, turning the desolation below into an open skyway. In the canopy, insects and small prey flickered between branches, and the shortest glide could mean the difference between capture and starvation. The ribs of Wageltosaurus arched outward like the frame of a fragile kite, and its scales bore grooves that may have anchored thin membranes. These ancient architects of air were not flyers in the modern sense, but experimenters in physics. Heat defined their world as much as hunger. Oxygen levels in the late Permian atmosphere fell to some of the lowest in Earth's history, dropping to near 15%, barely enough to sustain the metabolism of large animals. Those who rose into the air gained not only access to food, but a new way to breathe, exploiting cooler, oxygen-richer layers that lingered above the scorched ground. Fossil microstructures reveal traces of vascular networks dense enough to suggest warm-blooded endurance, a foreshadowing of birds and mammals yet to come. In dense stands of conifers and ginkgos, small creatures learned to glide between shadows. But as the climate grew harsher, vegetation thinned, and open spaces demanded longer distances to cross. This environmental stress pressed evolution to refine control. Fossils of early diapsids display subtle asymmetries in limb proportions and muscle attachment signs of steering, banking, and stabilization in mid-air. Where a leap once ended in a crash, it now ended in a curve. The air became not merely an obstacle to fall through, but a surface to be read and ridden. The first wings were not built for beauty or conquest, but for survival. They were thin, trembling instruments of desperation, evolved amid drought and extinction. Yet in that fragility lay genius. The same pressures that dried seas and killed forests also sculpted the structures that would one day lift birds, bats, and dragonflies into dominion over the sky. Insects, already masters of the aerial world, provided both inspiration and competition. The fossil beds of the Ural region preserved dragonflies with wingspans exceeding 70 centimeters, their veins arranged like networks of living glass. Against such dominance, vertebrate flight remained tentative, miniature, almost secret. Yet these early gliders occupied ecological gaps. Insects could not. Nocturnal hunters, ambush predators, and silent travelers between isolated oases. They filled the twilight zones where air cooled and dust settled, the liminal hours of dusk when the world turned bronze and motionless, and the faintest rustle might betray a life on the move. Some scientists believe that gliding originated independently multiple times across Pangea. The morphological variety ribs in Coelurosaurus, elongated fingers in Craniosaurus, extended flanks in Mesistotrachelos suggests parallel experiments rather than a single lineage. It was as if the supercontinent's stress cracked open evolution's imagination, prompting the same solution to rise again and again in different corners of the world. The phenomenon is recorded not in one fossil bed, but across continents once separated by an ocean, united again only in reconstruction. Each fossil is a fragment of wind made solid, a remnant of air turned to stone. Gliding, however, was only the prelude. The true innovation came when membranes and feathers, muscles and bones found harmony in motion. Late Permian and Triassic trace fossils hint at creatures capable of flapping-assisted climbing, the proto-flight of small archosaurs that would, millions of years later, give rise to pterosaurs. In their anatomy, the story of propulsion begins. Chest girdles thickened to anchor muscles, forelimbs extended in proportion to body mass, and energy metabolism spiked. What began as an escape from predators became an adaptation so efficient it rewrote the rules of movement. Over the parched basins, volcanic haze stained the light and thinned the air, while the pioneers drifted from tree to tree above the scars of ancient rivers. They hunted insects that themselves had evolved alongside fire, using the heat columns of burning forests as thermals. Life was adapting to a world of extremes, not resisting catastrophe but inhabiting it. Each flight was a dialogue between endurance and entropy, between the Earth's violence and the will to transcend it. Even the ground bore witness to this transformation. Trackways found in the Karoo Basin of South Africa preserve the prints of creatures that scurried between vegetation patches, interspersed with long, smooth impressions suggesting leaps into the air. The distances between these marks, sometimes exceeding 4 meters, imply that gliding was not a rare improvisation, but a habitual motion. Pangea, once unified by stone, was being reconnected through the air by the fleeting arcs of beings light enough to cross its fractures. As millennia passed, these experiments would culminate in the first vertebrates truly at home above the ground. The pterosaurs of the early Triassic would soon unfold wings of stretched membrane spanning several meters, their skeletons miracles of lightness and precision. Yet their origins lie here, in the quiet rustle of the Permian canopy, where necessity became invention. The invention of flight was not a sudden leap, but a long, trembling ascent, born in drought, perfected in silence, carried by wind. And so the air, once a force that shaped continents and seas, became a medium that shaped life. The same atmosphere that burned forests and scoured deserts now bore creatures that escaped its fury by embracing it. In the dim light of a dying age, when survival seemed a fleeting possibility, evolution discovered the sky. The fracture begins. Fault lines and futures. The air had grown thin, the skies quieter than they had been for ages. What had once echoed with wings and wind was now still, as if the world itself was drawing in a breath before speaking again. Across the surface of Pangea, the heat of the sun lingered on stone, fading into a silence that seemed eternal. Yet beneath that calm, deep within the unseen mantle, something ancient stirred, pressure rising where the planet's heart still burned. Pressure gathered where no living eye could see. For millions of years, the supercontinent had rested heavily upon the Earth's molten interior, its weight pressing down like a lid upon a furnace. Slowly, imperceptibly, that lid began to crack. The mantle churned with slow rivers of fire, their movements measured in inches per century, yet their consequences would reshape oceans and skies. Beneath the crust, heat swelled in rhythmic pulses, building tension in the lithosphere, bending it until its silence began to tremble. Through the continental crust, fractures began to form, first microscopic, then visible, then vast. The great sutures that had once welded together the world's former continents began to strain. Ancient mountain chains, born from collisions long forgotten, began to split at their roots. Minerals distorted under the burden of stress, quartz veins sheared and reformed, marking each pulse of tectonic unrest like heartbeats in stone. The Earth's interior was no longer content to remain buried. It wanted to move. In the vast rift zones that stretched across the heart of Pangea, magma began to rise, slow at first, creeping through fault plains, then accelerating as the crust weakened. These were the first whispers of a new world, rift valleys forming where there had once been desert, basaltic intrusions, threading through ancient granite like veins of fire. In what would one day become eastern North America and northwestern Africa, the land arched upward, strained, and began to separate. The heat from below was not yet destructive. It was a prelude. Minerals recorded the tension in their crystal structures. Zircons trapped helium isotopes that told of deep heating. Magnetic particles realigned as molten flows cooled, freezing in the direction of vanished poles. Every rock carried a record, written in pressure and temperature, in iron and oxygen. Radiometric dating of these layers reveals the story, still the first faint signs of rifting, that began nearly 200 million years before our time. Each datum is a note in a slow symphony of rupture, a melody that played across millions of silent centuries. At the surface, the changes were almost invisible at first. Rivers shifted course, drawn toward new depressions in the land. Lakes appeared in fault basins, where crustal blocks sagged. The atmosphere, once a mirror of stasis, began to stir with volatile gases leaking from below. Steam hissed through cracks, sulfur tinted the air, and the scent of minerals drifted upward where water met magma. Life continued, but something had changed in the rhythm of the world, a faint tremor that echoed through roots, bones, and stones alike. Species followed the fault lines, unknowingly drawn to their boundaries. Reptiles basked along the new lake shores, and insects hovered above hot springs that bubbled where the crust thinned. The ecosystems of Pangea adapted to the instability beneath them, thriving in the geothermal warmth that bled through the fractures. Even as the surface seemed steady, the patterns of life were being redrawn by forces they could never perceive. Nature had begun to adjust to separation before separation itself was complete. Every tremor carried a warning. In the deep geological archives of what would become the Central Atlantic magmatic province, lava would one day pour across half a continent, flooding plains and burying forests beneath black stone. But in this earlier age, That violence was still forming, pressure without release. Gases accumulated in chambers, CO2 and methane rising in concentration, hinting at the climate upheaval to come. The Earth was preparing for a purge, and every crystal, every fault, every shifting plate was part of that preparation. And beneath it all, in the unseen dark of the mantle, the true architects of change continued their slow revolution. Mantle plumes rose in columns of heat, softening the crust, guiding the fault lines toward eventual fracture. Convection patterns twisted beneath the lithosphere, pulling at Pangea's seams. The energy that once united the continents was becoming the very force that would tear them apart. What began as a microscopic strain would soon become continental drift. Even the magnetic field of Earth began to waver during this time. Reversals became more frequent, their traces found in ancient basalt flows that preserve the dance of poles across the globe. Such fluctuations may have mirrored the instability within the mantle, the heartbeat of a planet entering a new geological rhythm. Pangea was not just a continent breaking, it was a system rebalancing itself, seeking a new equilibrium in the face of its own weight. In time, great rift valleys would open, where now there were plains. The first outlines of the future Atlantic would begin as narrow fractures filled with basalt and brine. As heat escaped and pressure released, the supercontinent would breathe again, but at the cost of its unity. The land that had once been one would begin to drift towards separation, the edges fraying into the shape of continents we would later name. The fracture was both an ending and a beginning, the moment when stillness surrendered to motion. And in the quiet intervals between these colossal events, the earth waited. The forests swayed under strange winds, unaware of the cataclysm that brewed beneath their roots. The skies above were calm, but the ground was restless. The first fractures of Pangea were the preludes to extinction, the first whispers of the great dying to come. The world's silence was not peace, but pressure, a tension that sought release in fire, ash, and transformation. What had once seemed eternal was now trembling at its foundations. The continent that had stretched unbroken across the horizon was learning, once again, to move. Beneath the calm surface, a new story was being written, one that would end not with fracture alone, but with collapse. And in that collapse, life itself would be tested, reshaped, and reborn in the shadow of Earth's greatest upheaval. The great dying, when Earth nearly stopped breathing, the trembling deepened into ruin. From the seams of the world, fire began to rise, slow at first, then unrelenting, as if the planet itself were exhaling its buried heat. The crust split into vast fountains of basalt, each eruption pouring rivers of molten rock that buried valleys, erased forests, and darkened the horizon for centuries at a time. The air thickened with carbon and ash, the sun dimmed to a copper haze, and oceans once alive with coral and current turned sour and still. Life's great experiment, 1 billion years in the making, began to suffocate beneath its own success. Deep beneath what would one day become Siberia, volcanic fields sprawled across the land, larger than any the Earth had ever known. The Siberian traps, as they would one day be called, unleashed a cataclysm that defied comprehension. Millions of cubic kilometers of molten rock poured over the surface in waves of fire. Each pulse of eruption released gases that changed the chemistry of both sky and sea. Carbon dioxide thickened the atmosphere. Methane seeped from permafrost and seafloor sediments, amplifying the planet's fever. Sulfur clouds veiled the sunlight, bringing brief, deceptive winters before the world lurched back into a smothering heat. Across the globe, ecosystems collapsed in sequence. Forests first, then the rivers, then the sea. The lush lycopod groves that had once stretched across Pangea withered into ash. Rivers filled with silt and acid, their waters stained red by iron. Insects that had once thrived in the warmth fell silent, their delicate wings useless in the poisoned air. On land, synapsids, the mammal-like reptiles that had dominated the Permian, struggled to breathe, their lungs and hearts, strained by air, grown thin in oxygen. Those who survived the suffocating heat were undone by the scarcity that followed. In the oceans, the crisis deepened. Warm water carried less oxygen, and with circulation slowed by the stillness of the supercontinent, vast regions of the sea became dead zones. Trilobites, survivors of every extinction before this, disappeared forever. Coral reefs dissolved in the acidified shallows. Plankton populations collapsed, severing the foundation of the marine food web. With the ocean's breath cut short, predators starved in the dark. Fossil layers from this time show a world almost silent, black shales devoid of shells, bones, or movement. For centuries that stretched into millennia, Earth's pulse nearly ceased. Temperatures soared beyond what most life could endure. The skies rained acid, and the land itself bled methane from its frozen veins. The distinction between sea and sky blurred as evaporation and chemical haze wrapped the planet in a suffocating veil. From pole to equator, more than 90% of species vanished. It was not a single moment of death, but a long, choking quiet that crept across every biome, a planetary asphyxiation. Geologists reading the rock record see it not as a single line, but as a long shadow between worlds. The Permian layers below speak of abundance, thick beds of coal and fossilized forests, coral growths, and footprints of amphibians along lakeshores. Above, the Triassic strata begin thin and barren, a silence in stone. Between them lies the boundary, a horizon of charcoal and clay rich with iridium, mercury, and soot. Within this narrow band, the record of Earth's most profound transformation is sealed, a fingerprint of extinction that can be traced across continents. And yet, in that desolation, new patterns began to stir. Microbial mats clung to the edges of stagnant lakes, weaving thin green veils over the ruins of vanished forests. Cyanobacteria filled the newly vacant skies with the first tentative threads of oxygen once again. On barren plains, a few hardy survivors emerged. Small, burrowing therapsids that weathered the chaos underground, and the ancestors of modern conifers that sent new roots into ash-rich soil. Evolution, stripped to its foundations, began to rebuild from fragments. The survivors of the Great Dying were few, but their resilience would shape all that followed. The catastrophe had rewritten the rules of life, selecting for endurance over abundance, for adaptability over dominance. In the aftermath, ecosystems simplified, competition eased, and opportunity opened where collapse had cleared the stage. What emerged from the silence was a world reset, a crucible in which the blueprint of future life was forged anew. Scientists studying this period find its traces in isotopes and minerals. Carbon signatures that shift abruptly, evidence of an ocean starved of oxygen. Sulfur ratios that reveal volcanic winters and greenhouse ages alternating in rapid succession. These are not just numbers, but the echoes of a planet in distress. They show how fragile the balance of air, water, and life can be, and how close Earth once came to losing it entirely. Some models suggest the atmosphere may have held carbon dioxide levels 20 times higher than today's. Others show that temperatures rose by as much as 10 degrees across the globe. The oceans, heated and stagnant, may have produced toxic hydrogen sulfide gas, killing marine life and bleaching skies green with chemical haze. Each discovery sharpens the picture of a planet teetering at the brink of uninhabitability and of how long it took to draw back. In time, the fires waned, the floods of lava slowed, and the air began to clear. The carbon cycle, once broken, found its rhythm again as new plant life returned to the surface. Rain washed minerals into rivers, replenishing the chemistry of the seas. The world that re-emerged was no longer the lush Permian paradise that had been lost, but something leaner, stranger, and newly alive. Out of the furnace came the first ancestors of the dinosaurs, the earliest archosaurs, and the tentative beginnings of the age to come. The Great Dying was not only an end, but a pause between breaths, the still point before renewal. It stands in the fossil record as both warning and testament that life endures even when the planet forgets how to breathe. From the silence that followed, evolution would begin again, cautious but unbroken, testing the edges of survival in a world remade by fire. And from that devastation would come the slow reawakening life's most improbable recovery. Phoenix Earth, the Triassic Renaissance. For nearly 10 million years after the Great Dying, Earth's biosphere lingered in recovery. The oceans, once nearly anoxic, began to stir again as circulation patterns returned and oxygen levels rose. On land, ash and barren plains slowly gave way to the first signs of renewal. Hardy seed ferns, such as Dicroidium, anchored in the thin soils of the early Triassic, stabilizing landscapes stripped of root systems. The Triassic world was one of extremes. Temperatures remained high, and rainfall was erratic across much of the vast interior of Pangea. The continent's immense size meant that moisture rarely reached its central regions, producing great deserts like the one now recorded in the red sandstones of the American Southwest and North Africa. Yet, along coastlines and river systems, more humid zones began to flourish. The seas, too, were changing. After the collapse of most marine ecosystems, new lineages began to appear. Bivalves, ammonoids, and the first modern corals diversified rapidly, taking advantage of ecological niches left vacant. In shallow waters, the ancestors of ichthyosaurs evolved streamlined bodies adapted for fast swimming, marking a major evolutionary return to marine life among reptiles. By the Middle Triassic, creatures like Mixosaurus and Cymbospondylus dominated the open waters, feeding on fish and squid in newly oxygenated seas. On land, vertebrates followed a similar pattern of experimentation and renewal. The dominant herbivores of this period were dicynodonts and rhynchosaurs, sturdy, short-limbed animals capable of surviving dry conditions and feeding on tough vegetation. Early archosaurs, however, were beginning to rise in prominence. Fossil beds, such as those at the Karoo Basin in South Africa and the Ishigualasto Formation in Argentina, capture this moment of transition where synapsids and reptiles shared the same ecosystems, competing in a world still regaining its balance. The first dinosaurs appeared around 230 million years ago. They were not yet the giants of later ages, but rather small, lightly built creatures adapted for speed and endurance. Genera such as Eoraptor and Herrerasaurus represent this early stage of dinosaur evolution, possessing a combination of primitive and advanced traits. These animals were part of a larger radiation of archosaurs that would, over the next 30 million years, come to dominate both land and sky. Their success was rooted in physiology, lighter skeletons, more efficient respiratory systems, and upright gaits that allowed sustained movement across vast landscapes. While the reptiles diversified, another lineage pursued a quieter path toward endurance. The cynodonts, close relatives of the earlier therapsids, survived the extinction and continued to evolve into smaller, more adaptable forms. Fossils such as Thrinaxodon show features that bridge reptilian and mammalian anatomy. Secondary palates, differentiated teeth, and early signs of endothermy. These traits gave them an advantage in the fluctuating climates of the Triassic, allowing activity during cooler hours and greater flexibility in food sources. From these survivors, the first true mammals would eventually emerge, inheriting traits that would define the lineage through deep time. Flora played a central role in stabilizing this recovering biosphere. The spread of conifers, seed ferns, and ginkgos created new carbon sinks, gradually moderating atmospheric CO2 levels that had peaked during the end Permian volcanism. Coal deposits from the Triassic remain rare, a sign of continued ecological instability, yet the presence of soil horizons and root structures shows that terrestrial productivity was returning. Palynological evidence, microscopic fossilized pollen, reveals a steady increase in plant diversity throughout the Middle and Late Triassic, aligning with the reappearance of stable rainfall cycles in coastal and upland regions. The climate of the Triassic remained volatile, but showed trends toward equilibrium. Carbon isotope records suggest a gradual decline in greenhouse gas concentrations, while oxygen isotopes from marine carbonates indicate a cooling trend by the late Triassic. Volcanic activity, though persistent, was less catastrophic than during the Siberian Traps event, allowing ecosystems to recover in relative stability. This climatic moderation enabled the re-establishment of complex food webs, from primary producers to apex predators, such as the Rauisuchian's large, terrestrial archosaurs that ruled before the dinosaurs achieved full dominance. Continental movement subtly reshaped these worlds. Though Pangea still stretched nearly pole to pole, early signs of rifting began to appear in what would become the Central Atlantic region. Geological evidence from the Newark Basin and other rift zones shows volcanic deposits and sedimentary layers that record episodic tectonic stress. These first fractures marked the beginning of a process that would, over tens of millions of years, divide the supercontinent into separate landmasses. The ecosystems that developed during the Triassic would later find themselves scattered across continents, their descendants isolated and divergent, setting the stage for future evolutionary radiations. Insects and other small invertebrates also diversified during this recovery. Beetles, flies, and the earliest true bugs appeared in abundance, forming new relationships with the expanding vegetation. Their fossil record, preserved in fine-grained lacustrine deposits, reveals adaptations to pollination and decomposition, essential components of ecosystem recovery. This growing complexity of interactions between plants and animals signaled that Earth's ecological engine was once again running, producing new pathways for evolution and energy flow across the biosphere. By the late Triassic, roughly 220 million years ago, Earth was a planet reborn. Forests covered broad regions of the tropics and subtropics, while coastal lagoons teemed with fish, ammonites, and early marine reptiles. The skies were beginning to host the first true flyers, pterosaurs, descended from small archosaurs, whose membranous wings opened a new dimension of ecological space. The continents remained unified, but the living world upon them had diversified beyond recognition compared to the barren plains that followed the Permian extinction. Evolution, having paused on the brink of collapse, was now moving forward again with quiet determination. This was the Triassic Renaissance, a period of restoration and experimentation, where survival became innovation and adaptation became art. Every fossil bed from this era tells a story of recovery, of organisms reshaping themselves to meet new challenges. And though the scars of the Great Dying remained etched into the planet's rocks, the biosphere had regained its rhythm. From these resilient beginnings, the next great chapter of Earth's history would unfold. As the solid unity of Pangea began to give way to motion, once again the slow separation of lands that would birth the continents we now call home. A shattered unity, the birth of the modern world. It began with a shudder too deep to hear, the slow awakening of stone beneath a world reborn. In the quiet after the Great Dying, when forests once again reached toward a forgiving sky, the earth below began to strain. Beneath the rivers that cut through the Triassic plains, and the fern fields where early dinosaurs wandered, tension was gathering in silence, tension that would one day split the planet's face in two. From the stillness that had followed extinction, motion returned, and with it, the ancient habit of change. As the rift deepened, fire returned to the surface. Volcanic fissures stretched across what would become the heart of the Atlantic, spilling fountains of molten basalt that ran for hundreds of kilometers before cooling into blackened plains. The Central Atlantic magmatic province, born in this age, marked the first wound in the body of Pangea, a wound that glowed with heat and smoke for centuries. The gases it exhaled altered the air itself, warming and poisoning it in equal measure. With time, the fracture widened into oceans. Water found its way into the fresh scar, steaming and hissing against young rock, until narrow seaways became true depths. The Proto-Atlantic expanded like a heartbeat, pulsing outward from its spreading center. Yet, imperceptible or not, it was this quiet, unstoppable motion that would carve the world into the shapes we now know: Africa, the Americas, Eurasia, the scattered archipelagos of the Pacific. Far from the rift zones, life continued to evolve across the changing surface. Forests of conifers spread over the uplifted ridges, their roots binding loose volcanic ash to soil, while cycads and ginkgos filled the warm lowlands. The biosphere was reorganizing alongside the continents, each adapting to new coastlines, new climates, new boundaries of existence. Isolation became an engine of creation, and as the plates drifted farther apart, life diversified, transforming separation into opportunity. As continents parted, climate followed the pull. The breakup of Pangea created new ocean currents that began to sculpt weather in unfamiliar ways. Where once the supercontinent's heart had known endless drought, rain now returned, drawn inland by the formation of new shorelines. Polar regions cooled, and the equatorial belt grew lush. The Earth was breathing differently now, no longer in the single rhythm of a unified mass, but in the polyphonic pulse of a divided world. In the skies and seas, the results were visible in movement. Flying reptiles expanded their range, crossing newborn straits, while early birds began to claim the air as their own. On land, dinosaurs diversified into new forms suited to the landscapes of the Jurassic. Towering sauropods in the open floodplains, agile theropods hunting beneath conifer shadows. The fragmentation of Pangea became a crucible of evolution, shaping the destinies of lineages that would one day define entire eras. With each passing epoch, the world's map grew more recognizable. By 175 million years ago, the rift between Laurasia and Gondwana had widened into a true ocean basin, and new mountain chains rose where plates collided along their margins. The Tethys Sea opened between the northern and southern hemispheres, a warm cradle for coral reefs and marine life that flourished in its shallows. The Earth was redrawing itself with every eruption, every continental drift, every slow deposition of sediment along its new shores. And yet, beneath this vast reshaping lay an enduring continuity. The mantle still moved with the same deep rhythm that had formed Pangea in the first place. The same processes that tore continents apart were the ones that had once forged them together. The Earth was not destroying itself so much as rearranging its form, balancing heat, pressure, and motion in an eternal cycle. To the planet, unity and fragmentation were not opposites, but phases of the same conversation, one written in basalt and oceanic crust, in volcanoes and sediment layers. Shifts in atmospheric chemistry mirrored the world's new arrangement. The concentration of carbon dioxide rose and fell with volcanic activity, while oxygen levels fluctuated in response to expanding vegetation. These chemical oscillations left their trace in ice cores and isotopic records that scientists would one day study, deciphering the breathing patterns of ancient Earth. Through them, we learn that the breakup of Pangea was not a singular event, but a prolonged transformation, unfolding across millions of years, one that intertwined geology, climate, and life into a single evolving system. By the time the Jurassic had matured into the Cretaceous, the Earth had become a mosaic of continents moving ever farther apart. Ocean circulation strengthened, spreading warmth through the hemispheres. Coral reefs ringed the coastlines of newborn continents, and inland seas divided vast landmasses into island-like ecosystems. The planet was no longer dominated by a single, unbroken horizon, but by diversity of climate, of life, of geography. In the deep record of stone, this transformation remains visible. The symmetrical scars of the mid-Atlantic ridge, the basalt plateaus of Morocco and Brazil that once faced each other across an unformed ocean. Fossils found on opposite sides of the world still whisper of shared origins, identical species divided by time and drift. Through them, the story of unity and separation becomes tangible, reminding us that every continent carries a memory of the others. The world as we know it is not a collection of isolated lands, but the fragments of a once whole Earth, still moving, still changing, still connected by invisible tectonic threads. What was once a supercontinent had become a network of islands and nations in waiting, surrounded by deep and living seas. The motions that began with the first fractures of Pangea continue beneath our feet, imperceptible but unstoppable. The Earth, in its endless rhythm, reminds us that creation is not a single moment, but a continuum of breaking and becoming. And so the story of Pangea closes not in destruction, but in transformation. The unity that once defined the world gave way to diversity, and from that diversity, life itself flourished anew. What was torn apart did not vanish, but evolved into something larger, more complex, more alive. The continents we walk today are the living echoes of that ancient world, each carrying in its stones the memory of their long separation. From this parting, the modern Earth was born, and in that birth, the planet found a new form of unity, not in stillness, but in eternal motion. The ghosts beneath our feet, Pangea's hidden legacy. Long after the continents drifted apart, the shape of their unity lingered underground, etched into the slow rhythms of stone and heat. What once had been a single, seamless expanse of land left behind in visible architecture, the deep scars of rifts, the welded sutures of ancient collisions, the memory of pressure that shaped the bones of the planet. Though the oceans widened and mountains rose in new places, the story of Pangea never truly ended. It continued in the quiet, patient language of geology, where every grain of sand and ripple of basalt holds a fragment of that long-vanished world. Hidden deep in the planet's crust, the remnants of the supercontinent still sleep. Beneath the Atlantic Ocean, scientists have mapped the mirror edges of Africa and South America, their continental shelves fitting like the halves of a broken shell. Buried beneath these shelves lie bands of magnetic rock, recording in iron the moment when molten basalt cooled as Pangea began to tear apart. Each alternating stripe of polarity, measured through ocean floor magnetism, is a frozen heartbeat of Earth's shifting field, a perfect geological diary of the supercontinent's slow dismemberment. From the mid-Atlantic ridge to the Indian Ocean basins, these magnetic memories reveal the rhythm of separation that shaped every continent we know. Geologists tracing the world's magnetic memory have found evidence of something even older: ghost continents and sunken microplates that once connected now distant lands. Seismic tomography, which reads the interior of Earth like an MRI, reveals slabs of lithosphere that were pulled deep into the mantle when Pangea's edges began to crumble. These slabs, denser than the rock around them, lie stacked like lost pages at the bottom of the mantle transition zone, hundreds of kilometers below our feet. They are the fossilized roots of mountains, long eroded, and oceans long closed, preserved not in surface stone, but in the deep fabric of the planet's interior. In their shadows, geophysicists can still see where the forces of unity gave way to motion. Through computer-simulated mantle convection models, geophysicists have traced how these sunken slabs influence present-day volcanism and plate drift, acting as anchors that subtly redirect tectonic movement. Some studies suggest they still generate slow plumes of heat rising from the deep mantle, forming hotspots like those that fuel the Hawaiian and Icelandic volcanic chains, faint echoes of the tectonic scars left by Pangea's breakup. Far from the equator, in mountain ranges once joined, the echoes of Pangea's assembly remain visible in stone. The Appalachians of North America share their ancestry with the Caledonian ranges of Scotland and Scandinavia. Their rocks, when analysed, match in age, composition, and deformation. These once continuous highlands were born when continents collided in the Carboniferous, welded into a single chain that spanned thousands of kilometres across Pangea's centre. Today, separated by oceans and eras, they still rise from the same roots, testament to an age when the world was one. Even the minerals within their granites and metamorphic cores carry isotopic signatures that trace back to the same mantle source, confirming that their bond was not illusion, but inheritance. Layers of stone still speak of pressure shared and continents once conjoined. In Namibia, geologists study the Damara Belt, an ancient mountain system whose rocks bear the marks of the same continental suturing seen in Brazil's Ribeira Belt across the ocean. Microscopic analysis of zircon crystals, those near-eternal witnesses of geologic time, reveals identical isotopic ages on both sides of the Atlantic. Each crystal, no larger than a grain of sand, preserves the precise moment when magma cooled beneath the united crust of Pangea. It is through such infinitesimal records that we glimpse the continuity of continents, as though Earth itself had left behind a breadcrumb trail for those willing to listen. Even the air and the currents remember. The breaking of Pangea altered the planet's climate engine forever. When the supercontinent split, new coastlines and shallow seas redirected winds and ocean circulation, setting in motion the patterns that define modern climates. The monsoons of Asia, the arid belts of Africa, and the temperate zones of Europe all bear the fingerprints of that division. Climate models suggest that even today, the lingering shape of continental arrangement, the asymmetric spread of land between hemispheres, owes its balance to the tectonic inheritance of Pangea's demise. The weather, it seems, still breathes to an ancient rhythm. From species that walk to seeds that drift, life too carries the memory of that vanished unity. Fossil lineages tell stories of shared ancestry across oceans. Identical plant families once blanketed both Gondwana and Laurasia. Early mammal relatives and reptilian ancestors migrated freely before the continents drifted apart. Today, the descendants of those wanderers persist, as living fossils scattered across separated lands, cycads in both Africa and Australia, lungfish in South America and Madagascar. Even patterns of genetic divergence among surviving species reflect the timeline of tectonic rifting, marking where once continuous populations were split by new oceans. Evolution itself became an unwitting mapmaker, sketching the story of continental motion into the code of life. To study these traces is to read Earth's long memory. Every fossilized fern, every aligned mineral, every anomaly in the magnetic field is a word in the planet's autobiography. It is a text written not in ink, but in pressure and time, one that transcends human chronology and measures existence in millions of years. Modern science has only begun to decipher it, using satellite gravimetry and isotopic geochemistry to peer into what remains of the supercontinent's foundation. Through these tools, we come to understand that the Earth does not forget, it merely recycles, reshapes, and reimagines its own past. For the planet, nothing truly vanishes. The crust that once bound the world together has been folded, melted, and reborn countless times, yet its essence persists. Mountains rise where ancient sutures once ran. Volcanoes trace the margins of forgotten rifts. Even the continents themselves, though drifting apart, move in cycles that suggest future reunion, a Pangea reborn in some distant epoch, long after humanity is gone. In this grand continuity, there is a quiet reassurance that every fracture carries within it the seed of new creation. Beneath our feet, the ghosts of Pangea whisper not of endings, but of return. The next Pangea, the long future of continents. In the slowest clockwork of Earth, where millions of years pass like single seconds, the planet is already in motion toward its next great union. Beneath the crust, convection currents stir like deep ocean tides, pulling and pushing the continents with invisible patience. What we see today, the Atlantic widening, the Pacific narrowing, is the opening act of a drama that will not end for 250 million years. The plates drift at the pace of growing fingernails, yet the outcome of their dance is immense. A new supercontinent, the next Pangea, will one day rise. Far below the surface, the mantle churns with heat left over from planetary birth, a restless force that never sleeps. Every subduction zone is a promise of collision, every mid-ocean ridge a whisper of separation. Across the equatorial oceans, the Atlantic continues to spread, its central ridge marking the heartbeat of a planet still breathing through stone. But geologists foresee its eventual reversal. As the Americas drift westward and Eurasia turns east, the Pacific's slow contraction may herald its demise. This process, called subduction rollback, gradually draws the surrounding plates inward, sealing the ocean that once spanned half the globe. In its place, a supercontinent may form, centered roughly where the Pacific now lies. Some call it Pangea Proxima, Earth's next great reunion. Other models suggest a different destiny. In one vision, called Amasia, North America pivots northward, joining Asia across the frozen pole. The Arctic Ocean closes like a wound, binding two continents beneath auroral skies. In another, named Novo Pangea, the Atlantic continues to open while the Pacific collapses entirely, forging a world of vast interior deserts and new mountain chains along its seams. Continental drift, though imperceptible in human lifetimes, has left signatures that scientists trace with extraordinary precision. Using satellite-based GPS networks, geodesists measure the shifting of continents in millimeters per year, revealing how Africa moves north toward Europe and Australia slides ever closer to Southeast Asia. Seismic tomography, peering into the mantle like a CT scan of stone, shows vast plumes and sinking slabs, the circulatory system of a world in perpetual renewal. What emerges is a vision both alien and familiar, a planet destined to repeat its cycles, reshaping itself again and again through deep time. When the next Pangea rises, the face of the Earth will be profoundly altered. The supercontinent's vast interior, far from the moderating influence of the sea, will likely become a realm of extremes, blistering by day, freezing by night, swept by erratic monsoons. Mountain ranges will crumple upward where plates collide, perhaps higher than the Himalayas, and volcanic chains will stitch new land to old. The biosphere will respond, as it always has, by adapting, migrating, or fading away. In the deep future's supercontinent, the circulation of oceans will slow, and with it, the exchange of heat between equator and pole. Climate models predict that global temperatures could swing dramatically, amplifying drought in some regions and triggering ice ages in others. Species that survive will be shaped by isolation, their evolution guided once more by geography's firm hand. The cycles of unity and fragmentation that have governed life since the dawn of multicellular existence will begin anew, writing another chapter in evolution's endless story. Some scientists speculate that the next Pangea could influence the long-term fate of the planet's carbon cycle. As mountains rise and weathering accelerates, carbon dioxide may be drawn from the atmosphere and locked in stone, gradually cooling the world. But if volcanic activity dominates instead, the reverse could occur, a super greenhouse state driven by immense outgassing from continental rifts. The balance between these forces may decide whether the far future Earth resembles a lush greenhouse or a frozen desert, proof that geology and life remain inseparable even across aeons. The formation of a supercontinent is not only a geological event, but a transformation of Earth's identity. Each reassembly rewrites coastlines, reshapes ecosystems, and redefines the very rhythm of planetary life. The unity of land brings both connection and vulnerability. A single landmass is more exposed to the whims of climate, less buffered by the stabilizing effect of oceans. The biosphere, as it did after the Permian and Triassic upheavals, would once again be tested, forced to innovate in the crucible of change. On this distant Earth, familiar constellations will have shifted beyond recognition. The sun, slightly hotter than today, will pour more energy onto the surface, accelerating evaporation and altering weather patterns. Perhaps by then, humanity will have moved beyond its birthplace or vanished entirely, leaving only traces in the fossil record. Yet even without witnesses, the planet will continue its slow dance, reuniting the fragments of its surface in a silent affirmation that change is its only constant. The geologic clock that ticks toward this future is not something to fear, but to understand. Each cycle of breakup and reunion enriches the planet's complexity, shaping the diversity of life, the chemistry of oceans, and the pulse of climate. From Rodinia to Gondwana, from Pangea to whatever comes next, the pattern holds creation through motion, renewal through collapse. The Earth is both sculptor and sculpture, forever unfinished. One might imagine standing on that far future shore, beneath a sun 500 million years older, watching continents meet once again. The air would shimmer with heat, and the horizon might stretch across a land so vast that curvature itself disappears. Rivers would wander across an endless plain, their courses guided by the ghosts of vanished oceans. Somewhere beneath the surface, the same forces that once tore Pangea apart would be stirring again, preparing the cycle's next turn. And so, the story circles back. The unity once thought lost is never truly gone, it only changes form, awaiting its return. Pangea's legacy is not in the stones we walk upon, but in the motion beneath them, the eternal rhythm of drift and reunion. In that rhythm lies a reflection of something larger than continents, larger even than life itself, the planet's ceaseless drive to become whole again, only to begin the journey anew. Once, the world was whole, a single vast breath of land beneath an endless sky. Rivers wandered across continents that had not yet learned to part, and every creature walked a shared horizon. But unity is only a moment in Earth's long heartbeat. Even continents drift away. In the slow breaking of Pangea, we see the rhythm of change creation, born from separation, life reshaped by motion. The map of Earth is never still. Like, subscribe, and continue the journey the next lost world awaits.